Okay, then right. So thanks very much for the invitation. So I kind of know Chan Ho from the time when he was a postdoc at Stony Brook. So I'm glad that you thought of me for giving this talk. In fact, it's very nice because this topic is a very nice topic, this Hodge theory and Lagrangian fibrations, but some aspects of it may be a little bit complicated. So it's not so easy to present this topic nicely in 1 hour, but I think in 2 hours I can do a pretty good job. Okay, so see, let me find a way to move this thing out of the way. Okay, all right. So wait, sorry, I have to do one more thing here, make it full screen. Somehow it disappeared again. Okay. Okay, so I'm going to talk about the Hodge theory of Lagrangian fibrations. So let me say again, I mean, you probably saw this in the abstract that I'm a Hodge theorist basically, but I'm interested in using Hodge theory in algebraic geometry questions. So this will be an example of that. I will, most of the time I will talk about Lagrangian fibrations, but let me actually not start there, but let me start with the more basic example as a motivation to show some of the phenomena at work. So in this introductory part, there will be no Lagrangian fibrations, but I will just talk about the example of compact hyperkähler manifolds. This is not because the rest of the talk is about compact hyperkähler manifolds, because it isn't, but just because you see one or two of the phenomena that will show up later, but in an easier setting. Okay. So in this short part, X will be a compact hyperkähler manifold. A hyperkähler manifold always has even dimension, so I'll say that the dimension is 2 times n, this even number 2 times n. There's not very many examples of these things, so they basically all come from K3 surfaces or abelian surfaces, but the typical example is a K3 surface that would be a 2-dimensional compact hyperkähler manifold, and then you can make n-dimensional or 2 n-dimensional examples out of it by taking a Hilbert scheme of n points in the K3 surface. So this is a compactification of the space of n distinct points on the K3 surface that has dimension 2n. And the point is, when you say compact hyperkähler, it really means that there's a special kind of metric called the hyperkähler metric on it. But from the algebraic geometry point of view, it's not the metric that matters, but it's some holomorphic object. It's a holomorphic symplectic form. Okay, so the main thing is that there's a holomorphic 2 form that's denoted sigma on X. And this holomorphic 2 form is a holomorphic version of a symplectic form. So it is supposed to be non-degenerate. What this means is that at each point, it gives an identification between the tangent space and the cotangent space at that point. And globally, it means it gives an identification between the tangent sheaf and the cotangent sheaf. Right? And this works as follows. So if I have a tangent vector field, I can contract the tangent vector field with this 2 form and to make a holomorphic 1 form. And that maps an isomorphism. Okay. And then the other piece of data is because it's a Kähler manifold, I just pick a Kähler form. Again, this could be the Kähler form of this special kind of hyperkähler metric, but it doesn't necessarily have to be. Okay, and so the main principle I want to explain in this first part, and that will show up again later, is that when you put these 2 things together, the Kähler form and the holomorphic symplectic form, then you get some very interesting symmetries. And it's those symmetries that we want to study. Okay, so in the compact case, the symmetries are acting on the cohomology. So the basic thing there is the Hodge decomposition on this Kähler manifold. So the kth cohomology decomposes by type into these subspaces HPQ. And then HPQ is isomorphic to the qth cohomology of the sheaf of holomorphic P forms. Okay, and now there's 2 different kinds of symmetries. So the first symmetry is, they both come from these 2 forms. The first symmetry is I can act on cohomology by taking the wedge product with the Kähler form. The Kähler form is a form of type 1,1. So in this decomposition, it increases P by 1 and it increases Q by 1 when you wedge with omega. And then the basic fact from Hodge theory is that you have the Hart-Lefschetz theorem that cohomology in degree below the middle, in degree below 2n, is isomorphic to cohomology in degree above the middle, above 2n, by wedging with a certain power of omega. And in terms of types, it means that HPQ is isomorphic to H2n minus Q, 2n minus p. So that's one symmetry. Okay, this is a symmetry that you always have on any compact Kähler manifold. But now, in addition, we have this holomorphic symplectic form. And so we get an extra symmetry, right? Because the symplectic form gives this isomorphism between the tangent sheaf and the cotangent sheaf. And then by wedge product, it also gives isomorphisms between forms and complementary degrees. The sheaf of holomorphic P forms is isomorphic to the sheaf of holomorphic 2n minus P forms by wedging with the suitable power of sigma. Okay, and then if I think of the spaces HPQ as cohomology of the sheaf of P forms, then you see that I get another kind of symmetry, which now only changes the P. HPQ is isomorphic to H2n minus PQ. Okay, those are the two symmetries. It's a little hard to visualize just from these symbols. So let me show these symmetries in the picture. So, you know, the conventional way of showing these spaces HPQ is in the Hodge diamond. You arrange them like this: the 0, 0, 1, the zeroth cohomology at the bottom, the cohomology of degree 2n, 2n at the top, and then as you go, so it's towards the left, the holomorphic part gets bigger, and to the right, so the P gets bigger, and to the right, the Q gets bigger. So for example, this row in the middle is the cohomology in degree 2n, the middle cohomology that goes type 2n 0 all the way to type 0 to n. Okay, and then the first symmetry, the Hart-Lefschetz theorem, it works like this. So wedge product with the Kähler form omega moves you up 2 steps like this, because both P and Q increase by 1. And then Hart-Lefschetz is a symmetry around this horizontal diagonal here, right? It's saying that every HPQ space below this diagonal is isomorphic to this corresponding space above the diagonal. So it's, if you want, it's a reflection along this line. That's what the Hart-Lefschetz symmetry is. Right? In terms of numbers, you know this, right? Because the cohomology below the middle and the cohomology above the middle have the same dimensions by just Poincare duality, but actually it's the specific symmetry is given by wedging with a certain number of powers of omega. Okay, and then the second symmetry is the one from the symplectic form. This goes in a different direction, right? Because now wedge product with sigma only changes P. It increases the P coordinate by 2. So it moves up diagonally by 2 steps. And then the symmetry here in the second isomorphism is just a reflection along this slanted line here, this axis here. Okay, so altogether we get 2 symmetries from these 2 different operations. It's symmetric around this diagonal, and it's symmetric around this this bisector here, right? Okay, and now something interesting happens. So this I'll phrase as some questions to the audience here. So I have these 2 symmetries: the reflection along this diagonal and the reflection along this bisecting line. These 2 symmetries will generate a certain group. Can you see what group is generated by those 2 reflections? It'd be nice if someone from the audience could answer this question. Yes, or maybe in the chat if you don't want to say anything. You seem to have a chat also, right? What group is it?
Is it D4?
Say again, is it?
D4.
D4, yeah, the dihedral group. That's exactly, right? So it's the symmetries of the square that are called the dihedral group. So the dihedral group with 8 elements. Very nice. Okay, and then there's an interesting observation, which is this dihedral group of order 8, or D4, is actually a Weil group, right? Because it's generated by reflections. It's one of these reflection groups. The Weil groups usually correspond to some kind of Lie algebras. Do you happen to know what the corresponding Lie algebra is? Like which Lie algebra has as its Weil group D4? Does anyone know?
So is it A2?
Say again?
A2.
In the Dinkin diagram A2? No, it's not A2.
Oh, okay.
Someone else? This is not the kind of stuff I would know because I'm not a Lie algebra person, but of course in this case I looked it up, so I do know it. But does anyone study Lie algebras and knows the answer? No? Shall I say it? Okay, all right. So the Lie algebra is SO5 actually. So it's let's see, what's the, it's probably B2, I think. Or is it C2? Anyway, the name of the Lie algebra is SO5, the special, it's a Lie algebra of the special orthogonal group of rank 5 by 5 matrices, right? So of course this could be somewhat of an accident among small numbers, right? Like this dihedral group is the Weil group of this particular Lie algebra, but maybe it's an accident, but actually it's not an accident. So the Lie algebra SO5 really plays a role here. And so this is because there's a theorem by Verbitsky, which says if you have the cohomology of a compact hyperkähler manifold, like this is the thing we're looking at in this Hodge diamond, then this cohomology is actually a representation of the Lie algebra SO5 always. The way this works is that you know, the cohomology of a compact Kähler manifold always is a representation of SL2, right? And this is shown by representing the cohomology groups by harmonic forms and then realizing that these operators of wedging with the Kähler form and so on, they satisfy the right kind of relations to give you SL2. And what Verbitsky shows is that in the compact hyperkähler case, you can again use harmonic forms for the hyperkähler metric. And then you get several different operators from the different complex structures, and together they satisfy the relations for the Lie algebra SO5. Okay, and this Lie algebra has rank 2, and so the decomposition into weight spaces in this representation would be indexed by sort of 2 integers, and in this case the weight spaces are exactly these HPQ spaces. Okay. So in this Hodge diamond, you're actually seeing the representation of SO5, and each dot corresponds to one of the weight spaces. Okay, so this is what I mean by this principle, that if you take omega and sigma together, you will get some very interesting symmetries that you don't see otherwise. Okay, and so it's this kind of thing that I want to talk about in a different setting, not in the compact case, but in a non-compact case. Any questions? No? All right, okay. So then let's go to the actual topic, which are Lagrangian fibrations. The setting for a Lagrangian fibration is, I now take a Kähler manifold, which is not necessarily compact, and which doesn't have any kind of special metric on it. But what I keep from the previous section is the existence of a holomorphic symplectic form. Okay, so I will call this manifold M. M is a Kähler manifold, not necessarily compact. I'll fix a Kähler form for a Kähler metric. And then I will also assume that there's a holomorphic symplectic form. Again, this is a holomorphic form, which is non-degenerate and gives an isomorphism between the tangent and the cotangent bundle. And again, because of this symplectic form, the dimension is necessarily even. So the dimension will be 2n. Okay, in this case, there's no relation between the Kähler form and the symplectic form. They're completely independent of each other. And then a Lagrangian fibration, it's a holomorphic map to another complex manifold of half the dimension. So in this case, dimension n. And I ask it to be proper, so the fibers are compact, surjective, connected fibers, and I want the smooth fibers of this map, so the general fiber or the typical fiber, to be a Lagrangian submanifold, right? So the general fibers, the fibers will have dimension n for dimension reasons, and Lagrangian means that the symplectic form restricted to the fiber is 0, right? So literally, Lagrangian means this condition, sigma restricted to the fiber is 0, and the submanifold has to be maximal for that property, but because of the non-degeneracy, the maximal dimension that a submanifold with this property can have is n. And for dimension reasons here, the fiber does have dimension n, so it is actually Lagrangian, it's maximal. Okay, these things are sort of, if you want, they're kind of generalizations of compact hyperkähler manifolds. In the compact hyperkähler case, I just have a compact manifold. Here I have a thing which is not necessarily compact, and then I have a map to some base B, and B is again not compact, but the fibers are compact. So I can still talk about cohomology of the fibers in some interesting way. I will give some more specific examples later, but again, simple examples are, you can take a K3 surface, which is of course itself, which is holomorphic symplectic, and then some K3 surfaces have an elliptic fibration, so a map to P1 whose general fiber is an elliptic curve, and that's a typical low-dimensional example of a Lagrangian fibration. If you want higher dimensions, you can again take the Hilbert scheme. So take the Hilbert scheme of n points on S. That maps to the Hilbert scheme of n points on P1, which is Pn. And then this map is again a Lagrangian fibration. Okay, and then these are like compact examples. The really interesting cases are the non-compact examples, and I'll give an example of that in a moment. Sorry. Okay, so here's a kind of very schematic picture of what these things will look like. So what you should imagine is, first of all, the smooth fibers of a Lagrangian fibration are known to be abelian varieties of dimension n, algebraic varieties that are compact complex tori of dimension n. Okay, so this is what this picture shows. Like the smooth fibers, think of them as being tori, like in the case of an elliptic fibration where there are elliptic curves. And then the question is about the singular fibers. So the real interest in these Lagrangian fibrations is, what do the singular fibers look like? What happens near the singular fibers? And basically, the only thing that's known is that this map pi is always equidimensional. So even the singular fibers can only have dimension n. Usually for a map between algebraic varieties or complex manifolds, the fiber dimension of the singular fibers could be bigger. But in this case, all the fibers have dimension n. So the singular fibers are some kind of degeneration of these abelian varieties, but we don't really know what they look like. There is one case where you know it. This is for these elliptic fibrations. When S is a surface and you map to P1, there's a classification of all the possible singular fibers by Kodaira. But in general, in higher dimensions, there's nothing even close to a classification. And so this is really the interest of these things. Okay. Yeah. So the other thing is there will be like a special set in the base B, usually some kind of divisor, where there's over which the fibers are singular. And so this is the kind of thing that's drawn schematically in red. Imagine that there's some special hypersurfaces in the base B, some codimension 1 subsets over which the fibers become singular. Okay. So let me give one very interesting non-compact examples. I showed you 2 compact examples, but the main interest of this problem is in the non-compact case. And so the most important example of a Lagrangian fibration altogether is the so-called Hitchin system. So this Hitchin system, the manifold upstairs is the space called MND, and this is a moduli space whose points parameterize semi-stable Higgs bundles. So what happens there is that you have a smooth projective curve of some genus at least 2. And on this smooth projective curves, you look at Higgs bundles, which are vector bundles together with a piece of extra data. And this space parameterizes all the semi-stable Higgs bundles. Okay, and then there's a map to some affine space Cn, and this is the Lagrangian fibration. So this map is holomorphic and proper and so on. Okay, now just very quickly, what does this space look like? So the points are these semi-stable Higgs bundles. So a Higgs bundle is just a holomorphic vector bundle with a given rank n and a given degree d on this curve. And then the second piece of data, the theta, is a so-called Higgs field. So this is a linear map from the bundle to the sheaf of 1 forms with coefficients in the bundle. So if the bundle had rank 1, for example, then theta would just be a holomorphic 1 form. But in the higher rank case, it's some kind of matrix of holomorphic 1 forms, if you want. And then the condition to be a point in this moduli space is that this pair should be semi-stable. So this is, you look at all possible sub-objects, so sub-bundles with a sub-Higgs, where the Higgs field is the restriction of the Higgs field on E, and then there's a condition on the degrees that defines stability. And as long as the rank and the degree are co-prime, there's actually no strictly semi-stable ones. All of them are stable, and then this space is actually smooth. So it's a complex manifold. This space is interesting because it shows up in many different places in math. So the most famous one is the proof of the fundamental lemma by Ngo from 10 years ago. It also shows up in this P equals W conjecture by De Cataldo, Hausel, and Migliorini, which was proved last year. So this is a conjecture about the cohomology of this moduli space. And then it shows up in the geometric version of the Langlands program also. So this is a quite interesting space. And the way this moduli space is studied is mostly through this Lagrangian fibration, this map H. Okay, so let me say quickly here. So I'm not really going to say what this map H is and so on, but let me at least say heuristically why this moduli space of Higgs bundles is holomorphic symplectic. Okay, so this at least we can see this easily on the level of tangent spaces. So when we say something is holomorphic symplectic, what we want is we want a holomorphic symplectic form. So at each point of the space, somewhere on the tangent space at that point, there has to be this kind of symplectic structure, right? Stuff has to be even dimensional, and there has to be this kind of special non-degenerate pairing. And the way this works here is you can see this by varying the two components of the Higgs bundle individually. You can move the bundle E and you can move the Higgs field, right? If I change the bundle, then what I get is the tangent space, the space of vector bundles on the curve. And the tangent space is by deformation theories identified with H1 of the endomorphisms of E. And in this case, because these guys are stable and therefore have vanishing H0 and H2, you have vanishing H0, you can compute the dimension of this H1 by Riemann-Roch, and you find that it's this integer big N, which is 1 plus the rank squared times the genus minus 1. Okay, and then so this is how much dimension I can get by changing E. But then independently, I can change the Higgs field, and the tangent space, the set of Higgs fields on a given bundle E is, well, what I can do is I can vary basically this matrix of one forms, right? So it will be the space of sections of omega 1 tensored with the endomorphisms of E. And you see, because the endomorphisms of E as a bundle is self-dual, these two vector spaces are dual to each other by Serre duality. And so the second space, when I change theta, also has dimension N. So then altogether, the space of Higgs bundles has a tangent space that has dimension 2n, so it's a 2n dimensional space. And also the tangent space at each point looks like a vector space plus the direct sum, the dual of that vector space. So it looks locally like a cotangent bundle, right? And this is where the symplectic structure comes from. So the symplectic tool form is the one where you pair, if I have two tangent vectors, it means I have two things in this H1 and two things in this H0, and then just pair them with each other in the obvious way. Okay, so this is the holomorphic symplectic structure. So the point of studying these Lagrangian fibrations is in particular to understand this Hitchin system. And so we do not want to assume that the space, the manifold M, is compact for this reason, because in this Hitchin system, it's not. The only thing that we can assume is that the map, the Lagrangian fibration, the map is proper, it has compact fibers. Okay, are there any questions on this example? And this is really well studied, but usually the way people study is that they look at a certain subset of Cn where the fibers are reasonably nice, and then they say stuff over that nice set. And you'll see one point of the result that I'll present to you is that it will work over the entire Cn. There won't be any restrictions on the fibers or anything. Okay, so what's the goal of the talk? So as I said, I want to study arbitrary Lagrangian fibrations. And I'll be interested in particular in the Hodge theory of this map, the Hodge theory of the fibers. I want to relate holomorphic objects on M and certain kind of constructible objects on B. And I want to study the symmetries that come from the symplectic structure, from having the Kähler form and the symplectic form and how they interact. Yeah, okay, I said that, yeah. So if I forget to pause and to ask for questions, please interrupt at any point, right? And if you have any questions.
Sorry.
Yes.
So base space, I will always assume it is smooth.
I will always assume that the base space is smooth because I want to, for my Hodge theory sort of arguments, if necessary. People do consider Lagrangian fibrations where the base is not smooth. Yes. Yeah. But the arguments I'll do, I do need to assume that B is a manifold. Okay. All right. So then let me go to the third part. So this is kind of still in the introductory bit. This is an older result by Matsushita that will show the sort of flavor of the type of result that I want, right? So let me maybe say what it is. So this Matsushita's theorem kind of used to stand on its own, but of course now and later in the talk you'll see that it's just a special case of some general thing. But this is a result about arbitrary Lagrangian fibrations, and again the point of this result is that it works on the entire base B. There's no restrictions on the fibers, right? So what it says is take a Lagrangian fibration and look at the push forward of the structure sheaf, but in the derived category, so as a complex, right? So R pi lower star of the structure sheaf. And then Matsushita says that first, this splits into a sum of sheaves. And then secondly, the sheaves that you get are actually the sheaf of forms on the base, the sheaves of holomorphic forms on the base, right? So this says, for example, the push forward of the structure sheaf is the structure sheaf. The R1 push forward, where you take H1 along the fibers, gives you the sheaf of one forms on the base, and so on. Okay, and so this is a kind of prototype for the result that I want because it's very uniform on B. It doesn't single out the special points where the fibers are singular or anything. It's just a statement that works on all of B. Okay, and I will say a little bit about what's behind the proof here. I won't give the proof exactly, but I'll try to give the sort of principle. Okay. So the first claim is that this derived push forward splits into sheaves. And this is actually just plain Hodge theory. This is a theorem by Kolar, right? So the point is, I look at sigma to the n, the nth power of the symplectic form. That's a nowhere vanishing holomorphic form of degree 2n. So this is a nowhere vanishing section of the canonical bundle. So therefore, the canonical bundle is trivial. So actually, when I'm saying R pi lower star of OM, I'm really actually looking at the push forward of the canonical bundle. It's just that the canonical bundle is isomorphic to the structure sheaf. For the canonical bundle, there's a result by Kolar that says that the push forward of the canonical bundle always splits. Okay, so in this case, because the canonical bundle is trivial, it says that the push forward of the structure sheaf splits. So the splitting is a kind of classical result. This is proved by some using Hodge theory along the fibers and so on, but anyway. Okay, so this is kind of if you're in the subject, if you know some Hodge theory, this is a familiar result, I suppose. So geometrically, the main point of Matsushita's theorem is that the first push forward of the structure sheaf is the sheaf of one forms. Then you can start taking wedge products, then the second push forward will be the second wedge power, so it will be omega-2 and so on. So the main point that we have to explain is why R1 pi lower star should be the sheaf of one forms. Right now, if you think along the fibers, this is a little strange, right? Because the R1 pi lower star of OM, the way you think about that is 0, 1 forms along the fibers, H1 of the structure sheaf along the fibers. Whereas sections of omega-1b are holomorphic forms along the base. So there has to be some process that somehow exchanges the fiber directions against the base directions in this Lagrangian fibration. Okay, so I'm going to explain the geometry of that. It's quite nice. So the way it goes is like this. So we'll construct a map from the sheaf of one forms to this push forward. Okay, so we start by taking a holomorphic one form on the base, just locally. We'll take an open set in the base, take a holomorphic one form on that open set, pull it back by the Lagrangian fibration, then it becomes a holomorphic one form on the pre-image upstairs, on the open set upstairs, right? And now we want to transform this holomorphic one form into a form of a different type. And this is something that we can do using the symplectic form and the Kähler form. So first, a holomorphic one form can easily be converted into a vector field because the tangent sheaf and the sheaf of one forms are isomorphic on a holomorphic symplectic manifold, right? So I have the symplectic form. The symplectic form gives an isomorphism between the tangent sheaf of M and the sheaf of holomorphic one forms. And by that, I can convert my pullback form into a vector field. I'll denote that vector field by V of beta, the associated vector field. And it's just given by, it's the unique holomorphic vector field so that when you contract with the holomorphic 2 form, you get this holomorphic 1 form pi upper star beta. Right? This is a pretty obvious thing. I mean, that's how you use sigma. You convert tangent vector fields to 1 forms and back. Okay, so then I've used sigma, but now I can also use the Kähler form. Like the Kähler form does the same kind of thing, actually. I can take the Kähler form, which is a form of type 1,1, and I can contract it against my holomorphic vector field. That eats up the holomorphic part of the Kähler form and leaves me with the holomorphic with a 0,1 form. Right, so do this contraction, contract the vector field against omega. It gives you a 0,1 form that I denote f of beta for the associated form. There's a minus sign for some technical reason, but doesn't really matter. Anyway, because everything is holomorphic, this thing is now is still closed for d bar. So it's a d bar closed 0,1 form. So it gives you some cohomology class in H1 of the structure sheaf, right? And so then if you take that and restrict it to the fibers, you get a morph. This process defines a morphism of sheaves. You can take a 1 form on the base, pull it back, convert it to a vector field, convert it to a 0,1 form, restrict it to the fibers, and then you get a map of sheaves like this. And then Matsushita is saying that this map of sheaves is actually an isomorphism. Right? So this is the process that relates those two things. Right? So it's, if you want, it's kind of, it's the same idea again as at the beginning, right? I have to use both the symplectic form and the Kähler form in order to do stuff, but then I can make some very interesting translations among things. Okay, and yeah, so this is the map. You know, then you have to do a little bit of work to show that it's an isomorphism, but at least this is the construction of the map. Yes, I think I want to say one other thing, which is this is not relevant for this process, but there's actually an interesting little comment, which is that the vector fields that are being constructed here, these V of betas, they're actually tangent to the fibers. So that there you really see that stuff sort of changes direction. If you think of the 1 form downstairs, you pull it back, it's a 1 form that's trivial on the fibers, right? But after I do this contraction against the symplectic form, stuff sort of gets rotated and the corresponding vector field is now tangent to the fibers. So when the form is trivial on the fibers, the corresponding vector field is tangent to the fibers. And again, this is a little calculation here. So if I go to a smooth point on one of the fibers, then the tangent space to the fiber is a maximal subspace, a maximal isotropic subspace. So a maximal subspace with the property that sigma is trivial on the subspace. That's the Lagrangian condition, right? And now the way I constructed my vector field, sigma is actually trivial whenever I take that vector field and I pair it with any tangent vector to the fiber under sigma, right? Because sigma evaluated on my vector field and any tangent vector is by definition of the vector field is the same thing as evaluating the pullback of the form on this tangent vector, but then the tangent vector is tangent to the fibers, and so that vanishes. So this shows that at every point, the vector field must be in the tangent space to the fiber, because I could add it to this tangent space and still get a subspace on which sigma is identically 0. And the tangent space to the fiber is by definition a maximal subspace like this. Okay, so this shows that this kind of rotation that you get by contracting with sigma, it changes the horizontal and the vertical directions. And interestingly, in case you have been wondering about this, this also shows that the tangent bundle to the fiber is trivial. And because I can pick a set of n independent 1 forms near that point, on the base, and then I'll get a set of n independent vector fields along the fiber. And so they will span the tangent bundle of the fiber at every point, so the tangent bundle is trivial. And this is how you show that the fibers are compact complex tori, for example. It's by this process. Okay. Anyway, so this is Matsushita's theorem, right? So let me maybe go back one more slide. So the main point is that what it does is it says the push forward of the structure sheaf gives me the different sheaves of forms downstairs, and that happens both at the smooth points but also at the singular points in a very uniform way. So this is the kind of result that I like. Any questions? Yeah. Okay. So then let me come to the last part of the before the break, I guess. So I won't really present any actual results in the first half, but I want to explain what the problem is about the Lagrangian fibrations. And so the problem, there's different ways of explaining it, but maybe the nice way is to present it in a slightly as a little mystery. So the mystery is that there's some kind of strange analogy on these Lagrangian fibrations between holomorphic objects and topological objects. Okay, and so this I'm going to explain now. Okay, so again, we take a Lagrangian fibration, arbitrary, pi goes from M to B, M is a manifold but not compact, B is a manifold but not compact. I already said that the smooth fibers are n-dimensional abelian varieties, and then I can take the cohomology of the smooth fibers. Right? The abelian variety is a very simple cohomology. So what I get in this way is that on the set, on a set B minus D, which is the subset of B where the fibers are smooth, the cohomology groups of these abelian varieties give us a variation of Hodge structure, right? Because the cohomology of an abelian variety has a Hodge structure of weight I, and so the ith cohomologies fit together into this local system, Ri pi lower star of Q. I will call that Vi for variation, and this is actually a variation of Hodge structure of weight I. Now, it's actually a very simple variation because it's completely determined by just the H1, right? I know that the cohomology of an abelian variety is just the second cohomology is the second wedge power of the first cohomology. The ith cohomology is the ith wedge power of the first cohomology. So the subspace HPQ in the Hodge structure of an abelian variety is just the pth wedge power of the H10 times the qth wedge power of the H01. And so the Hodge bundles in these variations, they are just actually wedge powers of the 10 and 01 Hodge bundles, right? The VPQ bundle in these variations is the pth wedge of V10 tensor the qth wedge of V01. And now Matsushita's theorem actually tells us what these objects are, right? V01 is just the 0-1 cohomology along the fibers, so that's just the push forward of the structure sheaf. And Matsushita gives us that this is omega 1b, the one forms of B. The 1-0 Hodge bundle is the holomorphic one forms along the fibers. I don't directly know what that is, but I know that it's dual to the previous one. Since the previous one is omega 1, the second one has to be the tangent sheaf, the dual of the omega 1. And so then I get that the Hodge bundles are just tensor products between the pth wedge product of TB and the sheaf of holomorphic Q forms. They're very simple bundles. Okay, so this is what happens over the smooth locus. There's no big mystery, right? And now what I want to do is understand how these things behave on the entire base, including at the singular fibers. If I add the singular fibers to the picture, then of course I will not get variations of Hodge structure anymore because stuff will degenerate and so on. So if I want to add the singular fibers, the best way to do it is to go to this larger setting of perverse sheaves and Hodge modules and so on. I'll say a bit more about that later, but for the time being, let me just say that the way you work with this in practice is that by applying the decomposition theorem. So this map is a proper map. I still look at the push forwards of the constant sheaf on M. And whereas previously I got these Hodge structures and Hodge bundles, now I just get a collection of perverse sheaves that I call P sub I. The decomposition theorem says that when you take the constant sheaf, you shift it a little bit to make it into a perverse sheaf, and then you push it forward. then it decomposes into a bunch of objects that are called PI and that are perverse sheaves on the base. Those are generalizations of these variations of Hodge structure. If you know a little bit about this topic, then you may ask, well, so this map pi is just a proper map between Kähler manifolds. Doesn't the decomposition theorem just only hold it for algebraic varieties or something? But actually, the decomposition theorem does hold for proper maps between Kähler manifolds. So this is by Saito in the projective case, and recently by Takuro Mochizuki in the Kähler case. Okay, so I can apply this. And so what we want to do is we want to study these PIs, these perverse sheaves that show up here. Okay, so each of these PIs is a perverse sheaf on the manifold B. The restriction to the smooth locus, to B minus D, is just this local system on the n plus ith cohomology of the fibers. Okay, the indexing here works in such a way that everything is normalized at 0. So the middle cohomology of the fibers is P0. This is the Rn pi lower star of Q. And then you can go down all the way to the 0th cohomology of the fibers. This would be I equals minus n. And you can go up all the way to the 2nth cohomology of the fibers. This would be the Pn. Because all the fibers have dimension n, there's no cohomology outside of that range. So all of these PIs, they're concentrated in between minus n and n. Again, between the 0th cohomology of the fibers and the 2nth cohomology of the fibers. Okay. And well, what this decomposition theorem tells me is, again, there's an interesting symmetry among these PIs. So first, the PI, it vanishes when I is bigger than n, okay? On the open set where things are smooth, the rank of PI is just the dimension of the n plus ith cohomology of the fibers, and that's 2n choose n plus I, because it's an abelian variety of dimension n. And then the difficult sort of analysis bit in the decomposition theorem is that when you act by the Kähler form, you actually get a map from PI to PI plus 2, right? Think cohomology in some degree on the fibers, and then in degree plus 2 by wedge product with the Kähler form. This is the relative version of acting with the Kähler form in the compact case. And there is also a relative version of the Hart-Lefschetz property. It says that the cohomology below the middle and the cohomology above the middle is again isomorphic by wedge product with the Kähler form. Okay, so PI, P minus I, which is the cohomology in degree n minus I, is isomorphic into PI, which is the cohomology in degree n plus I, by wedging with the Kähler form I times. But this happens now along the fibers, and it happens including at the singular fibers. Okay. Okay, yeah, sorry, no. Okay, now, so now this is the, and this is, I mean, these results are very difficult results, but they have been proved by Saito in the 90s and then by Mochizuki more recently. So this is a lot of, a lot of difficult stuff and analysis and so on goes into this, but once you have it, well, you have it. People have done it, so this is known. And so now I can tell you this curious analogy. So the curious analogy is that something very similar to all of these properties happens for the holomorphic forms on M, right? Each of the properties here on the left has an exact analog for the sheaves of forms on M. Again, if I look at the sheaves of holomorphic forms, they go from degree 0 all the way up to degree 2n, because M has dimension 2n. So if I center them around the middle one again, I can write them as omega n plus k, and then k can go from minus n to n, from 0 forms, which are functions, all the way to top forms, which are 2n forms. Okay, and so omega m n plus k is again only 0 in this particular range because m has dimension 2n. Well, omega, the sheaf of forms, is the wedge product of the sheaf of 1 forms. So the rank of these holomorphic bundles is also 2n choose n plus k. Just like over here, the generic ranks are 2n over choose n plus I. Right on the left, it comes from the fact that the fibers are abelian varieties. On the right, it comes from the fact that M is a manifold of dimension 2n. That's quite different. Wedge product with the Kähler form has an analog because I can take wedge product with the symplectic form. That also increases the holomorphic degree by 2. And then the really strange, really curious thing is there's an analog of the Hodge-Lefschetz property, right? If I take the wedge product with sigma, I get an isomorphism between forms in degree below n and forms in degree above n, which formally looks exactly like this Hodge-Lefschetz property over here. Stuff below the middle and stuff above the middle is isomorphic. Okay. And so the task is sort of to understand this analogy. Is there anything to this? Is this just a coincidence, or is there some actual deep math behind it, somehow that explains it? Okay, so the goal is try to relate these two objects. So pi for I equals minus n to n, and omega m n plus I for I equals minus n to n. And try to relate them in such a way that we can explain, for example, why there is a Hodge-Lefschetz theorem on both sides. Now, initially, it seems a rather strange idea, right? Because they're completely different objects and they live on completely different spaces. Pi is a perverse sheaf, so it's a kind of topological object. It's just the cohomology of the fibers. The sheaf of forms is a coherent object, right? It's a holomorphic vector bundle. Pi lives on the base B, but omega m lives on m, right? So it seems hard to imagine you compare those two things because they're different. They're like apples and bananas, and the apples are in one country and the bananas are in another country. So it's difficult to say anything about how they're connected. But nevertheless, there are some pretty precise conjectures by Maulik, Shen, and Yin from some paper from 2 years ago and last year, where they were trying to set up kind of relationship between these two. Okay, so what I want to do in the second half of the talk is I will explain how you can really relate those two things. So this goes through Hodge theory, more precisely Hodge modules. I'll try to give you a very precise statement of how they're related, like an actual theorem that says, you know, two things are the same and one thing is constructed from P and one thing is constructed from omega. And then I will explain how once you can relate them, you get some very interesting symmetries again that are sort of like the symmetries in the compact case. Okay, some interesting symmetries that relate those two Hodge-Lefschetz theorems and give us some action by some Lie algebras and things like that, which kind of opens a whole new perspective on these Lagrangian fibrations that was sort of not known before. Okay, so it's not quite half the time, but I will end the first half maybe and take a little break, and then before getting into a somewhat more tricky stuff. Okay.